Hello, everyone. Welcome. I'm super excited to hear from Gavin Piccione about all sorts of things. Gavin did his undergrad work at Stony Brook and then went to UC Santa Cruz to work with Terry Blackburn. And I think most of this work is from your PhD like basis, and then half and half. Okay. And then moved on to Brown, where he's a postdoc with Danny Barra. Gavin thinks about all sorts of things. Gavin and I are working on developing collaborations around Antarctica and paleoclimate. So that's some of what he'll talk about today. So he thinks about ice dynamics, the basal environment, ice bed interactions, paleoclimate, and all that exciting stuff. Gavin also thinks uses low temperature geochemistry tools applied to weathering and biogeochemical cycles. So he wears other hats as well, although I'm partial to the glacial environments that he studies. So let's welcome Gavin.
I think it's on. Okay. Is it on? Can you hear me? Great. Okay. Thank you, Ruthie, for the introduction. Thank you all for being here and for having me give the seminar today. Really excited to talk a little bit about the work that we've done through some, as Ruthie said, some of my PhD work on Antarctica, but mostly, or half the talk will be postdoc work thinking about the Antarctic ice sheet and how it responds to climate in the past, specifically looking at the rock record and trying to add a little bit more information from what the rocks have to tell us. And so you'll see, but despite my title, I'm not only looking in the late Miocene, I'm going to talk a little bit more in the Quaternary as well. So we'll have that in store. Okay, so a little bit of background about Antarctica and why I care about it. So Antarctica is obviously a continent. It's 99% covered by ice. So this is a continent scale ice sheet. Here's the contiguous United States for scale, so quite wide. It also is quite thick. So if we drew a line across Antarctica and looked at it in cross section here on the right, you'll see that the ice sheet is more than a mile thick in most places. So it's quite a lot of ice over geologic timescales. When Antarctica grows and shrinks, you partition water from the continent to the oceans and back. And so climatologists and also paleoclimatologists think about the growth and retreat of Antarctica in terms of sea level. So to give us a little primer on this is a figure from the most recent IPCC report with years on the x-axis between 1980 and 2100, and Antarctic mass change on the y-axis, and its equivalent sea level contribution through these 100 or so years of time. And so a lot of folks are looking at the ice sheet on human timescales, looking at what it's done in the last 40 years, and we see that ice loss has accelerated. But in terms of a sea level contribution, it really hasn't been, it's a few millimeters so far, but we'd expect that going into the next century, depending on the emission scenarios and the sensitivity of the ice sheet, it might contribute more and more to sea level. But I just want to draw your attention to the uncertainties on these data. And so the contribution of Antarctica to sea level is something that's still a bit of an open question, and we're trying to add parameters and constraints to the sensitivity of the ice sheet to try and help the modelers to do their thing and do their projections. And so I'm a paleoclimatologist. I think about timescales that are much further back in time than these next 100 years, but a lot of the motivation for my work is to try and understand the processes that allow Antarctica to grow and shrink and how the links between those processes and climate. And so that is sort of a motivating question for this work. And as a paleoclimatologist, we look at how Antarctica has changed in the past. And so the timescales we're looking at are, say, the 100,000 year timescales. So this is the benthic Delta 018 record from Lysecki and Ramo, now a canonical climate record. And so what we've seen over the past 800,000 years is these 100,000-year glacial interglacial timescales. And so understanding what the Antarctic ice sheet has done over those timescales is somewhat of a paleoclimatology question. And then over million-year timescales, it's even more fuzzy back in time. So if we look now, instead of the last 800,000 years, over the last 60 million years over the Cenozoic, the benthic record tells us a lot about these large-scale climate shifts where you have ice sheets sort of going from the early Eocene, where there wasn't much terrestrial ice, and over the last 60 million years, we built up the terrestrial ice sheets through time with some punctuated events like the growth of the Antarctic ice sheet at the early Oligocene transition, and all the way to the Quaternary, where you have large northern hemisphere ice sheets, as well as ice in Antarctica. So sort of the some of the questions I'll be asking about today are both what's happening over the Quaternary and what's happening on these more million-year timescales. Specifically for this talk, I'll have two motivating questions. How sensitive is Antarctica to climate change on century to millennial scales? And two, how has the ice sheet volume changed over million-year timescales? And what can we say about that, the effect on sea level on those timescales? Okay, so starting off, as I said, I use the rock record to try and answer these questions. And a lot of my work has been using these sort of special rocks from Antarctica called subglacial precipitates. These are hand samples, they're centimeter in scale, and they are made up of calcite and opal, oftentimes layered calcite and opal. It's like you can see in this sample. And so to give you an idea of what these actually are, they're from Antarctica and they're precipitates, which means that they form in water, and subglacial meaning that water is below the ice sheet. And so looking at this in schematic view, here is a glacial trough. Oftentimes what we've seen from remote sensing is that there's a bunch of water at the base of the Antarctic ice sheet. It can pond and pool in bedrock depressions. And in these bedrock depressions, in these water bodies, this is where these chemical precipitates are forming. And so the fact that we have these samples can tell us a lot about the physical and the chemical conditions of subglacial water. But we don't get them from the base. We actually find them from the surface of the ice sheet. And so the way that happens is that over time, ice is flowing over these bedrock depressions. Eventually, these samples are plucked up into the basal ice. And where you get basal ice exhumed to the surface, like along the transantarctic mountains, you leave these samples where that basal ice has sublimated away. And these are called supraglacial moraines, these piles of sediment on the surface of the ice sheet. Anybody who thinks about meteorites, this is also where we find a lot of meteorite stranding surfaces. So these are little capsules of what the subglacial water looks like. We can also date these samples, which is somewhat helpful. So we've dated around 50 of these samples. And what we find are samples that formed over the last 6 million years. So here's a histogram with the number of dated precipitates on the y-axis over the last 7 million years. Most of the samples we've dated with uranium-series through to the late Pleistocene. We also have samples from the middle Pleistocene and the late Miocene. And so I'll talk about these late Pleistocene and late Miocene samples in this talk. Also, just in terms of sampling locations, we've found around 50 of these samples from these 10 areas, mostly up along the transantarctic mountains, but also on the margins of the ice sheet. Okay, so starting off with this first question, how sensitive is the Antarctic ice sheet to climate change on century to millennial timescales? So again, looking at these glacial interglacial cycles, we know a little bit about what Antarctica did on these 100,000-year timescales, mostly from the marine sediment core record. So this is just a little bit of a background about glacial interglacial cycles and what kinds of geologic records we use to answer these. So this is an example of the Wilkes subglacial basin up on the East Antarctic side of the continent. And there's been some really great work done on IODP cores offshore of these low elevation basins. And what they found are data that look like these. So here is core depth on the x-axis. This is a plot from Wilson and others in 2018. And over the terminations, these warm periods in Antarctica's history, they see a sedimentary response, both a chemical and a sedimentary response in these offshore records that essentially tell them that the Wilkes Basin has sort of retreated and re-expanded on these 100,000-year timescales. But again, I want to look at millennial timescales rather. And so if we zoom in on the last 100,000 years or 150,000 years, we also have these millennial cycles. Folks who work on Greenland might know these as Dansgaard-Osger events. You also have similar millennial cycles in the southern hemisphere of warm and cold periods every 10 to 2,000 years ago. So a question on this first part is, does Antarctica respond to these millennial climate events? And I'm going to look at two of these precipitates to try and answer this question. These are sort of thicker precipitates. They have many layers of opal and calcite. Again, the black and the orange are the calcite, the opal are in white. These two samples come from along the Ross Sea, East Antarctic side of the Ross Sea up against the Transantarctic Mountains. And the first thing we did was try and find the timing of the layering of this opal and calcite transitions. And so what we did was we first took these SEM images to tell us, sort of have a record of opal to calcite, trying to get a spectra of mineralogy here. And then we dated the samples along the layering. So each marker here is the location of a uranium-series age. And so to get a time series that describes the mineralogic transitions in these samples, we took these line scans across the fabrics. And so what we are left with are time series that look like these. So on the y-axis, we have calcium weight percent. This is basically the amount of calcium in the sample along this line. And so the high values are the calcites, low values are the opals. And then in terms of timing of these sample formations, the sample on the left side formed between 150 and 230,000 years ago, and the sample on the right side between 54 and 42,000 years ago. And our first order inspection of these time series, we found that the opal layerings happen sort of cyclically through time, where every 10,000 years on this left sample, we seem to have an opal layer, and every 2,000 years in this right sample, we seem to have an opal layer. And so we wanted to know what's causing this cyclicity, and we compared these time series to our climate record. And so now we have those, in these two graphs, we have those same precipitate mineralogy time series versus the curves that describe climate from ice cores. So this is the Epicodome C ice core record, and this is the Taylor Dome ice core record over these time spans. And just for visually looking at these, we found it striking that during the warm periods, we have calcite formation, and during the cold periods, we have opal formation in both of these samples. And so this was our first result from this work, is that these opal and calcite transitions seem to be correlating with these southern hemisphere climate cycles. And so there must be some link between the subglacial hydrology in these samples and the climate transitions on millennial timescales. And so just to try and understand what is actually driving these cycles, what drives this link, the next few slides, I'll just describe some of the chemistry of these samples, trying to understand what these mineralogic these mineralogic layers, are telling us about the subglacial environment. So here are some chemical data across the sample. The first two curves are from laser ablation. So this is across this line again, across the fabric. So calcium again, calcite high, opal low. And first, I want to draw your attention to the cerium anomaly. And I won't go too into what how this proxy works, but essentially the cerium star values are a redox proxy, where the high values are reducing conditions in the subglacial environment, low values are oxidizing conditions. And what we find is that in the opal layers, we have reducing conditions. In the calcite layers, we have oxidizing conditions. The second set of data down here are isotopes. These are the delta 18O values of these samples, with opal in the green boxes, calcite in the green circles. And what we find is that the opals form from waters that are around 10 per mil higher than the calcite values. And so our takeaway from this is that we likely have two separate waters that are forming opal and calcite, where opals are forming from waters that are higher in oxygen composition, calcite forming from samples that are lower in oxygen composition. So interestingly, if we look at where these samples formed, up along the Transantarctic Mountains, and we think about what the delta 18O values of the ice in those areas should look like, we find that these values are quite a bit lower than what the ice in those areas should be. So to sort of point that out, here is a map that is a model of Antarctic delta 18O values, the ice compositions in these areas. And up along the Transantarctics, we'd expect -30 to -35 per mil values. And what we're seeing is the calcites are actually a lot closer to what the domes would be. Whereas the opals are, close-ish to the local values, where we can sort of surmise that this might be local precipitation. So taking this as a whole, our hypothesis is that what we have driving these changes in chemistry and driving our opal and calcite transitions through time is that we have this subglacial hydrologic change, where the calcites are forming from waters that are flushing from the interior of the ice sheet, while the opals are forming from local precipitation, likely also driven by a concentration mechanism to get high silicon values into solution. And so just to summarize, our hypothesis is that these samples are telling us about these flushing events, where each calcite layer is a flushing from the interior, and the opal is sort of the background condition, where we have lots of silicon in a sort of less hydrologically active environment. Okay, so we've talked about how these samples form and that they're linked to climate in some way. And so now the last few slides from this first part of the talk will just be trying to think about what actual link could be changing could link the climate to the subglacial environment. And specifically, this close coupling, we hypothesize, is telling us about some ice dynamic mechanism. How do you essentially take a millennial scale shift in climate and propagate that to the base of the ice sheet? So I'm going to be talking about Southern Ocean forcing as the hypothesis for what's driving this link. And so here's just a schematic of the Southern Ocean with the ice sheet on the left and the continental shelf. And for our purposes, what we're calling on are these warm circumpolar deep waters. So in the Southern Ocean, you have, this is a generalized schematic, but your surface waters and your deepest waters are cold, but your circumpolar deep waters are warm. And so there's been a lot of work looking at the fact that when you get these circumpolar deep waters up onto the continental shelf, you can drive melting at the edges of the ice sheet. And so in terms of our millennial scale forcing, during millennial scale cold periods, you have less upwelling of those circumpolar deep waters. And what that means is that you have a less active edge of the ice sheet. You have less melting on the edges, which allows for reduced subglacial hydrologic activity. During the warm periods, you have more circumpolar deep water upwelling, which is driving melting at your buttressing ice shelves and allowing your grounding lines to shift a little bit, which our hypothesis is that that's driving an increased flushing in the subglacial environment. And so just to summarize, we have these millennial scale shifts in our mineralogy. Those are linked in some way to our southern hemisphere climate, and our hypothesis is that thickening and thinning on the edges of the ice sheet is what's driving that. So returning to the question, is the Antarctic ice sheet sensitive? Does it respond to these millennial climate events? And we're finding that millennial scale ocean forcing is what's driving ice thinning, especially in these marine terminating outlet glaciers along the Ross ice shelf. Okay, so for the rest of the talk, I will be zooming out a little bit onto the million-year timescales, and this is where the late Miocene comes into play here. And just as a reminder, we have our benthic delta O18 stack, and on these longer timescales, especially when you get back into the Miocene and the Oligocene, we have a lot less constraint on what the ice sheet histories are doing. But what we can do, oh, sorry, let me just jump back here. What we can do is say that the benthic delta O18 record is essentially telling us what the ocean oxygen isotope composition is doing, is changing as a function of building ice sheets. So as you go through time, you get to higher values in the benthic record because you have more ice. And the way this works is essentially a global oxygen mass balance. The idea here being that there's a finite amount of water on the surface of the Earth. It's mostly partitioned between the oceans and the ice sheets. And each of those reservoirs has a different isotopic composition. So when you grow your ice sheet, you drive your ocean values to higher isotopic compositions. When you shrink them, they go lower. And folks have used this phenomena to do mass balance equations like the ones I show here on the bottom. So essentially the idea is that if you know what the mass of each of this reservoir is in the modern and the isotopic composition of each of these reservoirs, you can set it equal to some time in the past and solve for important aspects like the mass of the ocean, which can tell you about a sea level. So this is sort of a simplistic way of approaching this problem, but it's actually there's been a lot of work to use these sorts of mass balances and the benthic record to get at long-term sea level reconstructions. But there's a bunch of uncertainty that goes into this. So first off, we assume that we know pretty well what the ocean isotopic composition is through time from the benthic record. There's some uncertainty to that, which I won't get into in this talk, but you can ask me about later. I would say that most of the uncertainty comes from knowing the mass and the isotopic composition of the ice sheets. And so this work is trying to add some constraints to that by looking at the rock record and trying to get at what the isotopic composition of the East Antarctic ice sheet was through time. So specifically, we're seeking to add data on past East Antarctic ice sheet delta O18 compositions to better constrain ice sheet size and maybe get at a contribution to sea level. And in this case study, I'll be looking at the late Miocene from 6 to 7 million years ago. Again, going back to our precipitates, this is just a primer for what about the precipitates is important for this study, and that is the fact that these samples are forming in isolated basal meltwater ponds means that all of the oxygen that are taken up in these samples should be sourced from melting of the overlying ice sheet. So this is a hypothesis that we'll test, but is sort of the starting point for this work. Okay, so again, these are our samples in time. We're looking specifically at these late Miocene samples. And for anybody who thinks about chronology in the room, I just wanted to throw this in there. This is a Concordia diagram, which is showing our uranium and lead composition, and chronologists use this to get at uranium lead ages. And we were pretty excited to see that our samples are falling along this line in this uranium and lead space, which is telling us that the opals in these samples are very amenable to uranium lead dating. They're a closed system, and they're giving us good constraints on the ages of these samples between 6 and 7 million years ago. Okay, so sorry for the chemistry heavy aspect of this talk. I will try to go quickly, but I just want to give a quick primer into triple oxygen because I'll be showing triple oxygen plots. It's a relatively new proxy. But for folks who are interested, who have thought about oxygen in general, oftentimes oxygen is described as delta 18O. That's the 18 oxygen versus the 16 oxygen. Triple oxygen is just looking at the third isotope of oxygen, the 17O. What does 17O tell us about processes in waters on the surface of the Earth? So, oh, sorry, I don't want to pop to that. Oftentimes people will plot 17O versus 18O, and this is essentially looking at how these two isotopes are changing in space. And so here is a plot of some surface waters on the surface of the Earth. We have Vostok ice, which is Antarctic ice down here, modern snow values, which sort of array a line, and then tropical waters. And what we find is that if we're zoomed out like this, most waters on the surface of the Earth plot in a line on this plot. And this line is mass-dependent fractionation, essentially 18O and 17O changing with respect to each other along this linear slope of 0.528. And if every single water on the surface of the Earth fell on this slope, this proxy would be essentially useless because you'd just measure your 18O and you'd know what your 17O is looking at. And for decades, that was the assumption. But it turns out when you start to measure it at high precision, we find both mass-dependent fractionation, but also mass-independent fractionation. And so here I'm going to be plotting all of these water values on a CAP17O plot, which is essentially just the difference between the 17O in the mass-dependent fractionation and the non-mass-dependent fractionation. And so to summarize, this is all just to say we can use 17O to learn about fractionation processes in waters on the surface of the Earth. And for Antarctica, I'll take us through what processes those are. So most of the data I will be presenting on will be CAP17O versus delta 18O. I'll look at Vostok ice values and other sort of modern snow values, but what we need to know is mass-dependent fractionation on this meteoric waterline, mass-independent fractionation off of it. Okay, so we're interested in Antarctica, so getting us back there, these Vostok ice values fall in this distinctive space in really, really low values in delta 18O, and also this low array in 17O. And what we know about Vostok is that it's a core in the interior of the ice sheet. So thinking about the isotopic composition of the ice sheet as a whole, these low values in 18O are not surprising because they're in the domes. The 17O values, the fact that you have this array, is a function of the precipitation in this area of the ice sheet. So in ice sheets, the interiors, both in Antarctica and Greenland, are so dry and so cold that a lot of the precipitation is diamond dust precipitation. Essentially, you are crystallizing out water from the atmosphere, you deposit it on the surface of the ice sheet as snow and ice and then firn, and in that process, you change the 17O. So for our purposes, this is useful because it's a very distinctive space in triple oxygen space that tells us that we're looking at ice in this array. And so just one other thing to point out is that these values where they fall in this space are glacial to interglacial in time. So interglacial periods will fall up here on the global meteoric waterline. Glacial periods will fall down here off of it. And looking at this as a time series over the last 150,000 years, you can see that the delta 18O, which you've probably seen in ice cores, changes on glacial interglacial values, and so does the 17O. Okay, so what we're going to do with triple oxygen is we're going to compare precipitate triple oxygen values to Vostok to test whether they represent the composition of ice. Last thing before I show you the data is that I'm going to present the data as the water values that the samples formed in, but this is going to require that I do a fractionation correction from the solid phase to the liquid phase. So essentially, I measure calcite and opal, but I do this correction to get back to water values. And these are empirically derived corrections that we know pretty well. But the important part is that these are temperature dependent. And so what we've done is we've measured the clumped isotopes in the calcite of these samples to tell us about the temperatures at the base of the ice sheet. We assume that opals form pretty close in temperature. And what we find is that, sort of unsurprisingly, the samples are forming between 0 and -8 degrees Celsius. So we use those to go from our calcite values, which are the curves here, and map those onto water values. Okay, so thank you for bearing with me in all of that chemistry. Let's actually get back to the results of this work. Finally, the triple oxygen plots. Here's that same plot I showed, cap 17 versus delta 18O, now with our Pleistocene oxygen composition. So these are only the precipitates that are in the last 350,000 years. I've measured triple oxygen in the opals, and I'm showing here the calcite values. I've not measured triple oxygen in the calcites, just delta 18O. Okay, so the opals are falling right on Vostok, which is great for us, where we have confidence now that the hypothesis that oxygen in these samples will be little archives of what the ice is actually showing us. And both the calcites and the opals are arraying values that are between about -60 and -45. So these are sort of what you would expect for interior ice compositions in the Pleistocene. But if you remember back to where these samples are forming, again, this is consistent with the idea that these samples are actually forming from water or ice that are from the interior of the ice sheet. And so this will be important for our thinking about the Miocene samples, because our hypothesis is that the delta 18O of the precipitates represents a maximum composition of what your interior ice might have looked like. Essentially, to say that another way, there was ice that was at least as low as the precipitates are telling us during the Miocene. Could have been lower, but you had ice at least that low. Okay, so here are the Miocene values, and the take home here is that they are shifted towards higher values. Interestingly, the Miocene opals are also arraying a similar area in 17O space. So this is telling us that they are ice compositions, but they're at least 7 to 10 per mil higher. So our best guess for what the Miocene composition would have been is between -40 per mil and -50 per mil. Do I have till 11:30 or do I have till 11? Am I already 11:30? Okay, good. I looked up and I was like, oh no, I'm over time, but then I forgot. Okay, good. So the result here is that these Miocene samples are arraying a similar value in 17O space. They are telling us about the Miocene ice sheet, but they are shifted to higher values, which means that the East Antarctic ice sheet in the late Miocene time would have been higher than the modern values, at least 6.5 per mil higher. So this tells us that something about the ice sheet volume or geometry. And so for the next few slides, I will sort of zoom out and try to say what this composition tells us about the ice sheet size and maybe a little bit about sea level. But I just want to preface this with, this is sort of, this is preliminary work, and this is really what I got interested in working with Ruthie about, maybe applying ice sheet models to try and say, okay, if we have -50 per mil ice in the late Miocene, what can we really say quantitatively about the geometry of the ice sheet during this time? But at this point, I'm just going to say, okay, if we assume that this was the average value of the interior, how big was the ice sheet and how much did it contribute to sea level? And so just bringing us back, I'm essentially going to plug in my new East Antarctic values into this mass balance. I'll still have to assume something about the Greenland and West Antarctic ice sheets, but I will solve the mass balance and say how high was the sea level, what was the mass of the ocean. And again, I'm going to just assume that we know what the ocean composition was. This is an assumption, but this is also something we can sort of test with this knowing the isotopic composition of the East Antarctic ice sheet. Okay, so here are my here's my mass balance calculation. The results from that, on the x-axis, we have the East Antarctic ice sheet delta 18O. So this is our constraint. I told you that it was probably at the lowest -50, but just to allow for uncertainty, I've plotted it between -51 and -48. And solving the mass balance on the y-axis, I have sea level above present. So assuming that we know the East Antarctic ice sheet composition. And again, I said that I had to make some assumptions about Greenland and West Antarctica. Those are the two curves. So assuming a half deglaciated Greenland and West Antarctica, that's in green, and assuming a fully deglaciated Greenland and West Antarctica, that's in purple. But really the take home here is that if you know your oxygen composition of the ocean well, and if you assume that you know the ice sheet composition well from our values, you can start to get at a lot more precise values for what sea level might have been. So in this case, this is telling us you had between 9 and 4 meters higher of sea level in the late Miocene. And so adding a little bit more quantitatively to these sorts of questions in terms of what our compositions are of the East Antarctic ice sheet with models might help us to do these sorts of calculations. So just to summarize, East Antarctic ice sheet delta 18O can help add constraints to past sea level and at least ice sheet size and maybe past sea level. Okay, so here are some key takeaways from these two projects that I outlined. First, we're seeing that the Antarctic ice volume is sensitive to millennial scale climate changes because we have thickening and thinning on the edges of the Ross Sea, like I showed in that first part. The second project, we looked at the delta 18O of late Miocene East Antarctic ice sheet and found that it was around -50 per mil, suggesting that East Antarctica might have had less mass. And then finally, East Antarctic ice sheet delta 18O constraints can help add some context to ice sheet size in the past and maybe help get at sea level. Okay, so I have a little bit of time. I just want to plug a little bit of future work. So essentially, I told you about adding ice sheet delta 18O values with precipitates, but what I'm working at right now as a postdoc is trying to do this with volcanic rocks. So the idea here is that throughout the last 30 million years in the Antarctic ice sheet, you had volcanoes that have been erupting underneath it. And oftentimes they erupt into the ice sheet and melt at the ice in those areas. And this is a schematic from John Smiley, who has been really prolific in doing sort of geologic constraints on these glacial volcanic rocks we talk about. But essentially you have lava erupting underneath the ice sheet, oftentimes melting the ice in a really, really high capacity. They can even sort of poke through the ice in a lot of places. And you get these slurries of essentially glacial meltwater and lava water. And there we have these samples called hyaloclastites, which are these glassy volcanic samples. And the idea that I'm looking at is, again, looking at the triple oxygen proxy. Essentially, they're not as clean as the precipitates, right? Because I told you the precipitates only source oxygen from the melting of ice, whereas the glacial volcanic rocks source oxygen from the melting of ice and any sort of mantle volcanic oxygen that might have been there. But a hypothesis is that these samples would, instead of falling near the mantle values, would fall on mixing trajectories between mantle and oxygen. And in the triple oxygen community, people use these sort of mixing trajectories to get at what your meteoric water value would have been. So this is a potential. This holds potential as a way to expand the precipitate project to adding the delta 18O of the ice sheet through time in a lot of other different places. And so I've been working with Kurt Painter from Bowling Green. He had a bunch of these glacial volcanic rocks from Minna Bluff, again in this Ross Sea area throughout the Miocene. They look like this. These are like these glassy secondary minerals. This is chalcedony, which is what we measured. And so some preliminary work is showing, yes, we have these initial hyaloclastite triple oxygen data falling on these mixing trajectories. And what we're going to try and do is just add measurements to these and see if we can start to really array along these mixing trajectories, which can get us back to, again, same thing as the precipitates. What was the delta 18O value of the ice during these time frames? And these mixing trajectories would tell us that along the East Antarctic side at 9 million years ago, you had between minus 35 and minus 25 per mil ice, which kind of fits in with what the models might tell us. So with that, I'm on, oops, I went to my extra slides, but yeah, so that's sort of some future work, but something that we're excited about to try and fill in this record. So with that, I will take any questions. Thank you all for listening. I really appreciate it.
Could we have a student first?
That was a stretch for me. This is a really awesome talk. Thank you. I'm interested in the sediments and the erosion that's being produced from glaciers advancing and retreating. And I was curious if you've thought about, when you're linking this with an ice sheet model and the dynamics happening between the ice and the earth, if you could compare these different signatures of your water systems, because there's two, and if you look at the sediment record offshore, and if that has like any linkage between like active deposition and these like active water flushing systems.
Yeah, that's an awesome question. Something if I project my career in the next 5 or 10 years, I would love to answer that question, right? So essentially, we know a lot about what subglacial water should look like and what ice compositions chemically should look like. So you're exactly right. If we were to look at our offshore records, which we have a lot of around the Ross Sea, I'd expect that if you look in the right phases, you might see sort of remnants of glacial meltwater flushing or ice sheet loss. I think that I've tried to explore some of these ideas, and the one caveat to this is that it's hard to preserve these sorts of, there aren't very many phases in your sedimentary record that will definitely preserve an ice composition, but I think they're there. I think that there's been a lot of work looking at uranium, because subglacial waters are really rich in uranium, so that might be an avenue forward. I think really, though, the idea is like looking at measuring the right phase, right? Do you measure diatoms, because they can sort of feel the water composition offshore, but can be diagenetically altered, or do you measure things like oxides? Or it's definitely something we can explore, but you're exactly right. I think that there's some opportunity to take what we've learned about the subglacial environment chemically and try and find those signatures offshore. Good question.
Thank you. Oh, I'm not throwing it that far.
I love the talking box. It's got a microphone in it and everything.
So I'm just curious, because it seems like it's really important for getting these ranges of measurements. How well do we know the gray bar on that?
Oh yeah. So the gray bar is essentially through the last 15 years that folks have measured all kinds of water at the surface of the earth. They've empirically derived that gray bar. So that was that 0.528 slope. That was this gray bar. And I would say that for surface waters, for any types of precipitation on the surface of the earth, we know it pretty well, though it can change depending on if you're looking only at, say, tropical storms versus water at the poles. I would say, though, that because people have done triple oxygen studies on Antarctic ice, we know it pretty well for the poles. Through time, though, I guess that would be sort of a question. I think that there's not as much, say, values from the Miocene, so that would be an assumption of this work, and possibly sort of the type of work that people can measure in the rock record and sort of establish that a little bit further. But yeah, that's definitely an assumption we're making for the triple oxygen that's based on many modern measurements, but not as many through, say, the Miocene.
Right. And so what about even if you just go to, say, the last glacial maximum or any glacial epoch? Do we think that modern averages can still be used so that you
Yeah,
can pin
yeah.
it?
People have done a lot of measurements through the rock record and say I showed those Vostok values, and through at least the last 150 to say through the Quaternary, we know that pretty well that the processes that have mass dependently fractionated triple oxygen haven't changed too much to change the mass dependent line. So yeah, but that's a good question. It is something that
Yeah, thanks.
we have to assume for this work.
So I'm interested in geochemistry. So while you were trying to get past it, I have some questions.
Oh, excellent. Good.
With regards to the precipitate of the calcite and opal, do those precipitate out at like different time periods? Did you guys do precipitation models on that? How do eutectic temperatures play into that?
Yeah. So we in this first, in the paper I presented in that first half, we tried to think a lot about, okay, like how do you get calcite and opal to a first order? And it turns out to be a bit of a chemical challenge to figure out how to sort of monomineralically plot, precipitate calcite and then an opal. And we did, I don't have any of the plots here, but we did a bunch of geochemical modeling to try and describe this. And we also have a lot more chemistry data on the samples than what I've showed. But essentially, the idea is that to get opal forming in the subglacial environment, you have a lot of brines that form because essentially you have waters that sit in the subglacial environment for, say, thousands, if not hundreds of thousands of years. And they can get concentrated through both cryo concentration, so actually freezing out water at the surface or at the ice bedrock interface, and also just ongoing sort of silicate weathering in the subglacial environment. So you have a source of silicon for the opals that is sort of the background, and based on the geometry of the opal layers too, we know that it's forming as a colloid in these sort of brine-like environments. But in those environments, you have no carbonate. There's really no carbon source in a brine like that. But what people have been finding in a lot of subglacial environments, and we have sort of some carbon data to prove this for our samples, is that you have a mechanism to get carbon from the substrate into these subglacial waters in certain areas where you have microbial activity. So the idea for the precipitation mechanism kind of fits in with these flushing events where you have these brines forming at the edges of the ice sheet, and every once in a while you have a flushing of water from the interior that has a carbon source, and that drives precipitation of your calcite. So it's sort of this back and forth, and it requires a mixing of two fluids. And so that's sort of the geochemical models that we've done was to prove that that is a viable explanation for precipitation of these samples. I think that was your whole question. Is that?
Yeah.
Yeah.
Hi, thanks, Gavin. So the Pleistocene samples had this millennial scale variability and precipitation, and it looked like the Miocene ones also had these back and forth. So
Yeah.
is that millennial scale variability in the Miocene? In glacial interglacial variability?
Yeah, I would love to know that. You're exactly right. Like we have opal calcite layers in the Pleistocene, which we did all this work to understand, but they also are in the Miocene samples. We do not have the chronology to answer that. So the uncertainties in the uranium-lead value, the uranium-lead ages would be on the order of like 50 to 100,000 years. And when I started to produce these chronology, I was like, wait, maybe I could just produce a bunch of dates and drive down the uncertainties. But that I've not gotten there yet in terms of the chronology. So we don't have the data to say, but I'd love to sort of really pull that apart. It's a good question.
You can have both of them. Pick your pick.
So Marcy Phillips asks, a general question on the Lisaki and Raymer oxygen isotope curve, what accounts for the steep, sharp transition from max glacial to max interglacial versus the tapered stepping down from a max interglacial to a max glacial?
Yeah, that's a good question. That a question basically about the climate dynamics. So right, throughout the glacial interglacial cycles in the past 100,000 years, you essentially get terminations that go from in 10,000 years, you're into interglacial climate, but then you sort of taper off into glacial periods. That's an open question, I would say. Yeah, you essentially have these interplays between insulation driving your glacial interglacial cycles and teleconnections in your interior Earth system that are driving your 100,000-year cycles. And so essentially it takes longer to cool your Earth, but once you start to drive a termination, you can drive that really quickly. I won't do justice to this in a quick question, answer to this question, but I'll leave it at that. Yeah, it's a good question.
Hi, I'm a little confused about the millennial timescale variability, and you'll have to forgive me because I'm not a paleoclimate person, so I don't really know what the state of the ice sheet looked like during that time period. But that area that you're talking about, an ice flowing towards the Transantarctic Mountains, isn't really coupled to the ocean at all. Isn't the Transantarctic mostly blocking ice flow, like in our modern environment? And so are you thinking that it's through the connection of these like Transantarctic outlet glaciers that go to the ice shelf, and that's really responsible for that? And have you considered other hypotheses like variability and flux of the ice streams draining into the ice shelf, which can abruptly change flux of ice in those areas?
Mm-hmm. Yeah, that's a good question. So the hypothesis that we have is essentially that that in these outlet glaciers along the Ross Ice Shelf during these millennial timescales, that you're driving thickening and thinning specifically on the edges, which propagates its way up these outlet channels. And that was based on some thermodynamic models that we ran to try and say, how do you drive thermodynamically a change in the subglacial basal melt budget to get this change in water flushing. And the idea that we came to is that because it's under such thick ice, you need some shear heating, you need some motion of the ice through these channels that is driven on these millennial cycles and is linked to climate in some way. And so that's how we came up with a change in surface slope that is affected, or ice surface slope that's affected by thickening and thinning, specifically in these areas that you're like close to the outlets close to the marine termination of these outlet glaciers. Can you repeat the second part?
Lots of things that can cause thickening and thinning besides the ocean heating mechanism. And maybe, there's the coincidence of warmer temperatures at that time, but the grounding line fluctuates through that region. Is it possible that even the grounding line is moving through there, or that ice streams are turning on and off over time, on millennial time scales? And so, yeah, coming to that, like, how do you pinpoint exactly that it was the increased ocean heat? Right. Is my question.
Yeah, so I guess I would say that was the hypothesis we went with, just because we were looking for some link between exactly the ice processes, some mechanism to climatologically drive ice motion through these outlet glaciers. But I would say there is, this is a great question. I would love to explore this further, that really all we need is an ice dynamic response. That's the ocean was our best guess as to what would drive an ice dynamic response. So sort of like without a huge lag between a warming event and a hydrologic response at the base of the ice sheet. But I would be really open to other hypotheses as to what could possibly drive that. I would say I'm not married to ocean force.
I have a follow on, because you would actually need a lag time. I don't know what that lag time is, but you would need a lag time for a thickness change to propagate enough inland to get a slope change that would adjust your hydropotential And so it would be interesting to try to calculate what that lag time is to see if it is viable with your hypothesis.
Yeah, yeah. So I actually have, maybe I'll just show this. So this was the figure from the paper, and this is our basal heat budget model. And we were asking that same question, like so the resolution of our chronology is telling us that there's no lag on the order of like 10,000 years or even several thousand years. There could be centennial lags that we don't see, but at least we know that, if you propagate without any ice motion, that would take tens of thousands of years. So we need some ice dynamic response to help it through. But yeah, you're right. It would be
That's long enough.
Yeah, yeah. So I think you're right. So there's some open question to this, and I'd love to start to actually quantify these things a little bit better than we've done so far in terms of like taking an ice model and testing our hypotheses. Yeah. Cool. Thank you.